Hello, Math 7 students. This is Open Up Resources Unit 2, Lesson 8, Comparing Relationships with Equations this time. Our last lesson was comparing relationships with tables, but in the past we've used tables to write equations and to use them to solve problems, so now we're going to go a step further and compare relationships just with equations. You will see that we start by writing we are going to be utilizing some tables here to help us with those equations, but our focus is on the equations and just comparing those equations. To get started today, though, we do have a quick warm-up, notice and wonder, and we have these patterns here with the rectangles. So, online learners, you should pause the video now, give yourself a second to write down the things that you notice before moving on and writing down the things that you wonder. Pause the video now. All right, we're back. What are some things that you noticed? We'll start with what you noticed first before we move on to what you wonder. What did you notice? Carter. Okay. So you looked for a unit rate trying to compare width to height? And for each one of these, here it was 3 wide and 1 high. Here it was 6 wide and 2 high. And here it was, is that 9? 9 wide, 3 high. So either way, the unit rate is 3 wide per 1 height. Kind of a weird unit rate to talk about, but yes, that was consistent all the way through. What are some other things that you noticed? Do you see a pattern as how it's growing? How is it growing in the height? Dax? Yeah, for the height, it copies the layer above, kind of. So here we have this layer, which I can see right here, right? But then how is it different though? It's copied where? I still am not hearing or understanding. Okay. Okay, I see. You're seeing how the pattern is growing, which I do like. You can see that, hey, what we're doing here is we're going to take that and we're going to add another section here. And then to get from here to here, we just copy that whole thing down, which is absolutely correct. But let's break it down even simpler. Just look at the height. Here the height is 1. Here the height is 2. Here the height is. How is that height changing? Danielle? Good. We're just adding another row. We've been so used to looking at multiplication relationships that you guys don't even understand that this is just a simple adding one relationship. You guys want to think about it so much more complicated. How is that width changing? So again, I've got a width of 3, now I have a width of 6, and now I have a width of 9. Peyton? Yeah, we're adding 3. Three columns, 3 blocks. Good things to notice. What do you wonder? Anything that you wondered about this situation? Did it bring up any questions, Carter? Okay. Which makes me wonder another question. Is there a relationship in the area and perimeters? What is the area? What is the perimeter? Is there a relationship between them? Okay, and now let's move on to our next activity. It's just a nice warm-up, nice and easy. Get your brains ready to think and work hard today. We have this next section where In a previous lesson, we worked with converting meters and centimeters and millimeters, but what we're going to be doing now is converting other units. Our first one, we have an equation F equals 9/5 C plus 32, where F represents the degrees in Fahrenheit, that's the temperature system that we are most familiar with, and C represents degrees Celsius, which is what basically the rest of the world uses. And so, I actually have a fun story about this. When I was in high school, I had a friend who was an exchange student, and he was from Italy. And we'd always be driving in the car, and the temperature would show up on the, the display dash. But you guys are probably familiar with that this day and age. That was a really brand new thing. But he'd always see the temperature and think, oh my gosh, we're dying. How is it possibly 80 degrees? He couldn't comprehend that because he was thinking 80 degrees in Celsius is basically near boiling. He didn't understand how we were still alive. So he was having to figure out how to make those calculations and conversions to convert from the Fahrenheit that was displayed to the Celsius that he was more familiar with. And this is actually in reverse. This is going to help us go from Celsius, which you can see here on the left-hand side of the table, to Fahrenheit. So how do we do this? Well, we just use that equation. And the equation is F equals 9/5 times C plus 32. And this whole column is full of C's, full of Celsius. So we're just going to use that equation by saying the Fahrenheit is equal to 9/5 times C, only what is C? C is 20 here, plus 32. And notice how I wrote this. This is going to be incredibly helpful as we progress throughout the year. All I did is I just took the C and I substituted the value of 20. But in doing that, do you see how I put that 20 in parentheses? It's so that we don't lose the operation. Because now I remember that the operation here between the 9/5 and the C, or the 9/5 and the 20, is multiplication. And we just have to type that into our calculators. Go ahead and plug it in now if you haven't already done so. 9/5 times 20 plus 32. So F here is equal to, Peyton? 68. You guys all agree? Okay, good. 68 degrees in Fahrenheit. And now a temperature of 4 in Celsius. Same process. F is equal to 9/5 times 4 now, because I'm substituting that C for 4, plus 32. And what did you get, Gabe? 39.2. About the temperature today. And 175 degrees Celsius, again, the same process. F is equal to 9/5 times 175 plus 32. And what did you get, Carter? 347, is that what you said? You guys agree? Okay, awesome. So we were able to use the equation and calculate the temperatures for each one of these, the temperatures in Fahrenheit for each one of these temperatures in Celsius. And now let's move on to 2. It says use the equation C equals 2.54 N, where C represents the length in centimeters and N represents the length in inches. We're going to complete this table. So now I know the inches, I'm trying to find the centimeters, and the equation that we're using here, C is equal to 2.54 N, and the N is the thing that is changing. I've got these various amounts here that we're going to use for N, that variable. So when I have 10, I just plug it into the equation. C equals 2.54 N, but again, I'm putting it in parentheses because I'm just taking this and substituting that value. And again, it helps me realize when I put it in parentheses that the operation here is multiplication. So here, C Celsius is equal to, not Celsius, I'm sorry, centimeters is equal to, Siley? 25 4/10. And 8 inches is about how many centimeters? C equals 2.54 times 8 this time. Thank you, Dax. 20 and 32 hundredths. Are you guys checking all their work too? Checking their calculations? You guys getting the same things? Okay, Carter. 8 and 89 hundredths for 3.5. Okay, fantastic. Now, are these proportional relationships? When we're looking for a proportional relationship, we're looking for a way, is there a way that we can go across the table by multiplying? And if so, is it the same everywhere in that table? I want you to pause the video and think about this while the online learners discuss, are these proportional relationships? Is there a way that we can go from one column to the other by multiplying by the same number? Pause the video now. All right, what do you think? Are these proportional relationships? Tell me your thoughts. If you're saying yes, I want to know what is the constant of proportionality. Get me started, Carter. Okay, this one isn't, and this one is. Who agrees? Okay, why? Let's focus on the one that is first. That one's the easiest one, so let's focus on the one that is. Gabe. Okay, so you're already recognizing the relationship in the equation. I gave you that hint a couple days ago, and you're already recognizing that difference in the equation, and we'll get to that in just a second. Let's go the old-fashioned way. Let's pretend like we didn't have the equations, and all we have is just the table. How can I identify that this one is and this one is not? Dex? Exactly. Find that constant of proportionality. 25 and 4/10 divided by 10. And what do you get when you go 25 and 4/10 divided by 10? 2.54. No, honestly, since we saw the equation, we're not surprised by that, right? Okay, what's the constant of proportionality here? Is it a constant? Is it still 2.54? Because 8 times 2.54 is 20 and 32 hundredths. And 3.5 times 2.54 is 8.89. And again, we know that because that's literally the calculation that we did, isn't it? We took the 3.5, we multiplied it by 2.54, and that's how we got the 8.89. So we're able to find a constant of proportionality here. Is there a constant of proportionality here? Carter. Not even close, right? And yes, we can do this with some simple mental math just by rounding, and that is correct. But let's not round. Let's be precise like we were here. So what would we do? Here we took our 25 and 4/10 and divided it by 10, 25.4 divided by 10. So we should be doing the same thing here, and it should be, go ahead, Peyton. Perfect. Perfect. That is exactly right. So, and I love what she said. She said, for those online learners who couldn't hear her response, she said, I pretended like I didn't know what the equation was, and I just focused on the table, which is exactly what I encouraged you to do. Focus just on the table. Find the constant of proportionality. 68 divided by 20 is 3.4. Let's see if it works everywhere else. 4 times 3.4 should give us, what was that number again? 13 something. 13.6. Is 13.6 the same as 39.2? No, obviously very different, which is what Carter was trying to explain to us as well. And what about here? Can I take that 175 and multiply it by 3.4? What does it give us? 595? So did multiplying by 3.4 work every time? No. Just for fun, can we find the numbers that actually do work to multiply as we go across? Because we know that multiplying by 3.4 each time does not work. What is the number that will work for this row? What strategy can we use? I'll wait because we should have more engagement here. Here we found the constant, or what we thought was the constant of proportionality by dividing. We worked backwards. What strategy should we use here since I don't know how a 4 changes to a 39.2? Go ahead and discuss. I need more hands than that. Okay, so I didn't hear a lot or see a lot of hands, but I heard the discussion throughout the room. You said, well, we would take the 39.2 and we would divide it by 4 and we get 9.8. So if I have to go across the table by multiplying by different things, is this going to be proportional? Definitely not. And here, 347 divided by that 175 is a big, long, ugly number, 1.98, and so on. So this is not a proportional relationship. Can you find a way to multiply to go across? Yes. Is there also a very specific relationship? Yes, but is it proportional? No. And so tying that in together, Gabe already found exactly what we're going to be discovering in the summary, that the reason why this happened is, yes, we started by multiplying as we went across this table, but then we screwed it all up by adding. And that's the key thing here. So are these proportional relationships? The first one is not. Write your answer if you haven't already done so. The first one is not, because we multiply by different numbers as we go across. The second one is. Because we multiply by 2.54 each time. All right, and now on to our next one. Okay, so again, we've got some cubes here. Each of them have different side lengths. What we're going to be comparing is the total edge length for each of these cubes, the side length and surface area for each of these cubes, and the side length and volume for each of these cubes. Ultimately, with these three tables, we're looking for the relationships that are proportional so that we can write some equations for them. So it asks, how long is the total edge length of each cube? We need to envision a cube and how many edges there are so that we can figure out the total edge length. Specifically, let's take a look at this one. This would be 3. Oh, that's a bad color. Let me choose a different one. 3, but this would also be 3, and this would also be 3, and this would also be 3. What's the length of edges so far? 12 so far. Good, but that's not all, because we also have 3 in the back, 3 in the back, and 3 in the back, and 3 in the back. So now what do we have? We have 12 in the front, and we have the 12 in the back. But that's not all. What about this edge? And so how many edges total are there? We lost track, didn't we? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total edges. So 36, good. How did you get that 36? Real quickly, because I know you lost track when we were trying to add it all together. What did you do in your head, Danielle? Uh-huh. I'm lost. You're right. Everything is right, but I got really lost. I think you're saying that we've got the 12 here, right? So we'd have 12 again in the back, and then one more 12 together. Okay, got it. Oh, I see, because you're counting it like this. Yeah, okay, got it. Okay, what about here now? Let's see, we've got 5. Do I have to go through the whole process again? 5 again, 5 again, 5 again. Can we figure it out? How many edges are there again? 12. 5 again, 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 and 5 again. A quicker way of doing that would be, Dax, 5. Yeah, just 5 multiplied by 12. And 5 multiplied by 12 is 60. Hold on, did I hear you say this? Here we multiplied by 12, and here we multiplied by 12? Is that something that you said to me? Okay. And what about here, where now the side lengths are 9 1/2? Or, yeah, 9 1/2, 9.5. So 9.5, 9.5, 9.5, 9.5. I don't need to go through that whole process again, right? Because you know that all we have to do is take all 12 of those edges. Each one of those 12 edges is 9.5. Therefore, go ahead, Peyton. Beautiful. So what's going to happen if I have S? What is that going to be? Are we going to change our pattern, or are we still going to multiply by 12 as we go across? And so then we would have S multiplied by 12 to give me 12S. Okay. Man, that one was a little bit tricky for me. Let's see if we remember anything about surface area from last year. Do we remember anything about surface area? No? Okay. So, when we are looking for surface area, what we're looking for is if I had a present that's in that shape of that box, how much wrapping paper am I going to need to completely cover it? So, it's the area of the surface. And we know that when we're finding area, it's just length times width. Only if I'm looking for the area of just this face here, let me switch to a different color. If I'm looking for the area of just this face right here, that would be length times width, but the length and the width are the same, 5 and 5. So that's just going to be 5 times 5. But I don't have just this one face. I also have this face here on the top, this face here on the bottom, right? This face here in the back, trying to cover in that whole back there. This face here on the side, this other face here on the side that you can't see, and that's a lot of faces. So how many faces are there total? Imagine it, maybe get a box of your own, maybe get a little dice if you have a die, and count how many faces there are on that, and you'll know that there are actually 6. So yes, I can find the area of just this one flat piece right here. It's 5 times 5. So that would be equal to 25. But I don't have just one of those. I end up with a total of 6 of them. So it's the 5 times 5. But then I am multiplying it by the 6 different faces that we have. So I end up with 5 times 5 times 6, which is equal to 150. And these are going to be in square units, or units squared. And so what is it going to look like over here? So again, that same kind of idea. We have, if I'm looking for just the area of that piece right there, that's going to be 3 times 3, but I don't have just one of those. Count how many faces there are on that whole entire cube. There are 6 of them, so that's going to be 3 times 3 times 6, which is equal to 54 units squared. And moving on up here to the bigger one, same idea, except that this isn't just 9.5, it's 9.5 times 9.5, so that will give me the area of one of those faces, but I don't have just one of those faces, I have 6 of those faces, so then multiplied by 6, and I get 541 and 5/10, or 541.5 units squared. So what is that going to look like here? Where now, how big is this cube? We don't really know, but I know that because a cube is made up of all those squares, that it's going to be the side length multiplied by that same side length, whatever it is. And there are going to be 6 of those faces, so then multiply that by 6, and you get, be careful, because S times S is S squared, and then of course we take that and we multiply it by 6, so 6S squared. So what is the volume of each cube? What is the volume of each cube? Now the volume of each cube, again, this is like if you have that box, you have that little die and it's hollow and you need to fill it with water. How much is it going to take? Another way that you can think of it, I'm going to try and draw this for you. So we've got a box, and it looks like this, and I'm going to fill that box up. Let's make it more boxy. I'm going to fill that box up with a bunch of smaller little boxes, like the box right here. right? And we have a whole bunch of those all the way throughout the whole thing. And how many of those is that going to take? So for this would be a length of 5. This is kind of like the one that we have over here. So it would be 5 and then looks like 5 more. So think about that bottom surface, or maybe the very, very top surface. How many of those little blocks would we have? This is going to take me a second. 1, 2, 3, 4, 5. Right, we'd have 25, but there's going to be 25 on each one of those rows. One, 2, 3, 4, 5. So we've got layers of 25. So it's that 5 times 5, which gives us the 25. But then we've got 5 of those rows, so multiplied by 5 again. So what we're doing here is 5 multiplied by 5, because that's how many of those little cubes it would take to fill in that whole bottom layer, but we've got 5 layers that we're trying to fill up. So 5 times 5 times 5, which is going to be 125. And for the 3, the side length of 3, 3 times 3, but there's going to be 3 layers. So 3 times 3 times 3, which is 27. And the 9.5, well, it'll be times the 9.5. That'll be that many little cubes times 9.5 layers. So 9.5 times 9.5 times 9.5 is equal to 857 and 375 thousandths. So what am I doing here? Well, here each time I'm multiplying it by that side length, because that tells me how many of those little cubes I'm going to need per layer, but then we multiply it by that again because that's going to tell me how many layers I have. So this is going to be our S times S times S, or in other words, S cubed, because volume is given in units cubed, or cubic units. All right, so what I'm going to do now is I am going to ask you to pause the video and figure out which of these relationships is proportional. Make sure you're able to explain how you know, and then I want you to write equations for the total edge length E, the total surface area A, and the total volume V, using all of this information that we did here in the tables, which we've already basically done because I figured out how I'm moving forward in that table. I know how I'm going across. So I want you to pause the video and write those equations after you figure out which one is proportional. And what we have discovered is that there is only one relationship that is proportional. There is only one relationship that is proportional, and that is the edge. That's the only one that is proportional, because all that I'm doing is I'm taking this number and multiplying it by 12. That's the only one. It might have been tricky here because you think, oh, we're just taking it and multiplying it by 6, but we were doing something else first. We took that number, multiplied it by itself, and then multiplied it by 6. We took this number and multiplied it by itself, and then multiplied it by 6. And since these are all different, we multiplied it by 3 and then 6. We multiplied it by 5 and then 6. We multiplied it by 9.5 and then 6. So we are seeing something that is not proportional here. And here, again, it is not proportional because here I multiplied the 3 by 3 times 3, which is different than here where I multiplied it by 5 times 5, which is different than here when I multiplied it by 9.5 times 9.5, and so those numbers are changing. So the only one that is proportional is just the edges. So what are these equations? Well, edges, all we do is take that pattern that we already wrote for sides. The edges is E is equal to S times 12, or 12S. The area is equal to, we have that one up here for us as well, 6S squared. And the volume we also have, V is equal to S cubed. So figuring out and being so precise as we filled out our tables really helped us be able to write those equations. That's it for today. We will continue with the Are You Ready for More next time, so there's no homework this time, but we'll see you next time when there will be homework.